So, where have we reached so far? In our story, we have been discussing, very briefly go through this, discussing a case where we have a satellite orbiting the Earth and collecting, so that we have three types of sensors. We have sensors that measure reflected energy. Where does this reflected energy come from? We saw that it comes from radiation from the sun, and when this radiation hits the Earth's surface, some of it will be absorbed. Yeah, some of it will be absorbed. Some of it will be transmitted, and we said that the rest of it will be reflected, and that is what the satellite will get. After the atmosphere, the Earth has absorbed energy, it can be emitted, and we have thermosensors which we have thermosensors can emit radiation. So what I want is this, I don't want it that color. So we were saying that can eventually have emitted energy, but we can also have a case where we have, in this case, we said we're dealing with backscattered. After it has been collected by the sensor, is eventually relayed to a ground receiving station. Okay, so this is what we have done so far. We have whatever the energy we have got, it's relayed to the ground receiving station, and we looked at the different corrections, levels of satellite imagery, and today we want to essentially want to deal with what is here. We want to begin appreciating what happens there. We also, in our discussion yesterday, emphasized how we have passive remote sensing, and we can have optical remote sensing, where we're dealing with reflected energy, or we can have thermal remote sensing, where we're dealing with emitted energy, and then we have active remote sensing, where we're dealing with radar remote sensing, where we're dealing with backscatter. So that's where we are from last week's lecture. So we this week want to start appreciating what we refer to as image. The ways, having got an image, what are the ways that we can interpret this image? And so we have two approaches, is what we call visual interpretation, and we have digital. The idea behind visual interpretation is that we have various elements of interpretation. In other words, what is it that we are able to extract by looking at satellite image? We mostly apply visual interpretation on high resolution imagery, but this doesn't mean that we cannot do it on lower resolution imagery. So I will like to use for this part of the lecture some slides that I have been using for teaching elsewhere. And let me share that screen, unless there are any questions. Are there any questions on what we have done so far? So we're going to go through a couple of the elements of visual interpretation. And this is a scene from a satellite image. And as you can see, we have different features. And when you look at this image, can we tell what are some of the things we can identify? When you look at this, what can you identify? Does science mean that you can't identify any? Yeah, so what can you identify from what you can see? Can you see anything?
Buildings and roads, though they are kind of blurred.
So you can see buildings and you can see
roads.
And
yes.
Why you are able, yeah?
Buildings, because they are reflecting that white bit of the roof.
Okay. And what is the nature of the roads? They are not as bright. So that difference in grayscale is what is referred to as tone. That's one of the ways that we can distinguish between features when you have a satellite image, by looking at the tone and see how the various tones are. You have brighter tones, you have darker tones. Please remember that the variation of tone also depends on which portion of the electromagnetic spectrum the image has come from. So can anyone guess where this is? We have surveyors here. So to the left up there, you have Mulago Hospital, the white building there is Mulago Hospital. You have the roundabout, Pisufule, then you have golf course. I don't know if you see my cursor. This is Mulago roundabout. This is Mulago Hospital. This goes towards Kamocha. We have the golf course here, and this is the city. So, but the point that we want to emphasize here is the fact that we are able to distinguish our different features because of the differences in tone. So whichever band you work with, certain images will have higher reflectance than others. So for example, if we were dealing with near infrared, your vegetative surfaces will be a lot brighter than your buildings and everything else. The other element of visual interpretation is called hue. And what is a hue? Hue means color. Here we have this satellite image, which I've been showing you. I've showed you many times, and we can distinguish different features based on their color. You can see the different shades of green. We can tell the grasses, the trees, the roads, the tarmac roads, the maram roads. We can identify the roofs, the buildings, and we are capitalizing on the fact that different surfaces will have different hues or colors. That's what we are trying to take advantage of. Here we are referring to texture, and by texture we really mean roughness. So by looking at the different roughnesses within the satellite image, we can also harness that to help us distinguish between different features, which is ultimately what we want to do in remote sensing. We want to map, we want to identify features, you know. We have other applications like modeling, but we may not have time to go through that. These areas are different from these other areas, and because of that, we're able to distinguish between the different features. Here we have shape. We have different shapes here. We can see the shape here, and from here we can deduce that we're dealing with a water body. And because of this, you can compare it, you can contrast this with that, and say here we're probably dealing with a road, this is a river, and then these are probably farms. This that we're trying to use to distinguish between different features. Another aspect is pattern. We can see these patterns, and if this is a water, if this is a water, and we see, what do you think these are?
Wetland vegetation.
Yes, wetlands. And we are deducing that from, the patterns. So one time we had a project for mapping wetlands. We had these high spatial resolution images, and we were trying to identify all of these patterns. Of course, that was because we were now going to use, we were using these elements of visual interpretation to map these wetlands. So for you to be able to do that, you need to have an appreciation of some of these elements of visual interpretation. Yeah, so the project was about mapping of these wetlands, and we chose to use these elements of visual. Okay, yeah, so after digitizing, that was what the project was about. The whole idea behind association, if you remember the first, I think I'll use this better to describe the elements of association. If this is Mulago, it means that we're by association, This is Yusuf Lule Road, and it means that that's the road to Kamocha. What I'm trying to say is that you use what you know to surrounding. And we ultimately know that probably your golf course. So that is how we do our visual interpretation. When you get an image and you want to extract features of interest, sometimes we will also use association. If we have time, the video that we're going to go through will elaborate more on. Okay, so let's go back to our whiteboard. So as I told you, we have different ways of extracting information from a satellite image, and for starters, we have looked at rotation. Now we want to have a chat about rotation. From what we have been discussing, there we have said that if this is our electromagnetic spectrum, can have a blue, green, red, and have a thing is that we can have our satellite collecting that and that band, and we have different ways of manipulating these images to be able to extract information. And what we want to do ultimately is to be able to distinguish one feature from the other. And so we shall be looking at a host of techniques that we can use to extract information from one another. Let me just have a so we can have a case where we have our image and we have our and 1, 2, 3, 4. We could even have 5 by the way. So when it comes to digital image interpretation, we have cases where we can seek to extract information from one band. We can extract information from 2 bands. We can extract information from 3 bands. We can even do more than 3 bands. And I would like to go through them. We would like to see how many of these we can go through. So from one band, we have different approaches, and sometimes we call them, sometimes we have to start, we may need to do what we call image enhancement to be able to extract information of interest. So coming here, when we have one band, we can have filters, and when you come to image processing software, it's pretty straightforward case. We have our image, we apply a filter, and we have our filtered image. So you have your original, you apply a filter, and you have your product here. So filters come in so many ways, and we can discuss a couple of them. Let me start with something which is very, very easy. We can have, there are many. We can have an averaging filter, mode, majority filter, averaging, mode, majority, image happening filter. We can have age enhancers, age enhancement, and so on and so forth. So let me begin with an average. Let me do a mod. That will be a lot easier. So look at a case where these are fictitious values. We are having, we can also have a median filter. So let me start with the median one. It will be a lot easier. And we have a 3x3 filter. And let us say we have values here. Now I have just cooked up this value. So we have our original image. We want to apply a 3x3 median filter. What is our median? Median means middle value, and we're getting lost. So we're going to explore with a median filter. We had got some fictitious. So 1, 2, 0, 1, 3, 2, 0, 4, 1, 1. And we want to apply a 3x3 median filter. How would it work? But essentially, since it's a 3x3 matrix, what will happen is that we on our original image, we map out 3x3, and we list our 3 here. So when you arrange these ones, we have 0, 0, we have 3 ones, we have 2, 2, 3, 4. So in this case, which is our median of these values here? Which is the median value?
1.
1, 2, 3, 4.
It's 1.
So this is our median. So when we come here, we look at our values there, and we put it in the middle, and then we now go to the next here. If we arrange, we have 0 0, we have 3 1s, 3 2s, 1 4. So yeah, what would our median value be? I think it would be 1 again, not so?
Yes, it's 1.
And the process of moving in that order is what we refer to as convolution. So through the process of convolution, it works in an area, moves, works in an area, moves. When it reaches the end, we come down. Now you will realize that we shall, if we now after it has reached the end, it will now come down here. Here, our values would be what? 0, 1, 1, 2, 2. So here I think it is 2, and so on and so on. So we're using the median to populate what we have here. And so you will eventually have your image 1, 1, 2. Maybe here it would be 1. So once it's gone throughout the whole image, you will acknowledge that we have the edges which have, and how we usually do that is that it usually takes the value of, so it takes the value, that value. So that's how a filter works. It picks some aspects and removes others. We can have mode. What is mode? Mode is most frequent. So here it would be 1. Now here, where they're equal, you would have to come up with an algorithm of choosing which one. But how you would fill it is that you would fill it with, but you can also have an average, whereby we get these values, get the average, and our values are averages of that. And and we also need to know that you can change your filter size from 3 by 3, 5 by 5. Notice that it's always an odd number. The other thing that you need to know, we have filters which are age enhancers. So if you have an image with your buildings, and you apply an age image, we call it sharpener, it will make your edges more prominent. We also have what we call edge detectors. So let us say you have your image. Okay, yes, I can. So you have building there, something there. Let's say you have your image. When you apply an edge detector, what will happen is that your resulting image, will only look at this image and detect the edges. So it will detect that edge, it will detect that edge, and it will detect. So we have various algorithms which are edge detectors. I've had a case of, let me just give you this illustration. Yeah, now, you could have a case where we want to extract features from here. Maybe you have this image, you want to extract features. Additionally, especially you GIS experts, you'd want to digitize. You'd want to digitize these roads and the features, but you could also just extract. Apply a filter so that it extracts the edges. We once had a project for mapping of, I think it was Arua town at the time, from a satellite image. And so what we had to do was to get an image and extract, and with digitizing was going to take forever. So we applied filters. And what it would do is that it would extract the edges of features of interest, so that you have the road extracted, you have the building extracted, you have the trees extracted, and then if you put that in an AutoCAD, it would be a lot easier. So these are all sorts of filters that we can use in remote sensing. They're numerous, we can't exhaust them. And the other challenge is that your program is too tight, so we won't be able to go through all of them. So that is it about filters, but we also have other techniques that we can, and remember, so far we're dealing with enhancement of a single band. So it could be band 1, band 2, band 3, band 4. The other way by which we're able to manipulate an image is by manipulating what we refer to as a histogram. What is a histogram? Let's look at a case where we have our image, we have our values, can have a representation of our values here. If we were to make a histogram of what we have here is a very simple one. We have 0, 1, 2, 3, 4, 5. How many? And so let us say we have 1. So how many zeros do we have? 1. How many ones do we have? How many 2s do we have? 1, 2, 3, 4. Also here. How many 3s do we have? I think 1. How many 4s do we have? We have 2. How many 5s do we have? We have. So a histogram is essentially, so if we're dealing with an 8-bit sensor, it means that our pixel values range from, we'll have 256 values, and that means our values will range from 0 to 55. 0 referring to no reflectance, to 55 to very bright. So when we have a frequency distribution of 0 to 55, can manipulate the histogram, come up with very interesting manipulation. So this is your histogram. So if I may ask a quick question, supposing we are dealing with an image from 0 to 255, our midway point is 127. If we had our image, what do you think that image would look like?
It would look dark.
Yeah?
It would be a dark image.
Exactly. So this will give us a dark image because most of our pixels are in the dark range, and the same case there. If they are all there, it would be too bright. And remember, our aim is to be able to distinguish features, and so we can manipulate our histogram, hopefully come up with clearer images which can enable us to distinguish between different features. So for example, let us imagine we have a near infrared image. The thing about a near infrared image, we know that vegetation has high reflectance, water has low, and soil have medium. So if we are looking at an image, the dark areas, the places which would have black would refer to places, just do it like this. So where would have it dark, those would be the water areas. White would be the vegetative areas, and let us say not too dark would be so would have this as water, and then would have this as soil. So if you looked at the histogram, we're saying that this is 0 to 255. Our vegetation pixels would feature somewhere there. Our water pixels would be there because there is a dark, and maybe your soils would be there. So we can say that maybe this is vegetation is somewhere there, and our soils are there. So we can do what we call density slicing, and the idea behind density slicing is that instead of having all these values, we can say from 0 to 50, assign all values between here a value of 1, all values from 50 to 150, assign it a value of 2, and everything here assign it a value of 3, so that our resultant image will now only have 1, 2, and so anything between 0 and 50 will assign a value of 1, or whatever value that it should have. These ones will be because of the density slicing. So we have our original image, and from here we have create our histogram, we carry out density slicing, the resultant image is that. Where can this be applied? When we are making masks, I'm sure in GIS you've had to use a couple of masks. You may want to distinguish water areas from non-water areas, or built-up areas from non-built-up areas, and this is how you can make a mask through density slicing. Probably the other thing that I would like to talk about regarding enhancement of the image, of a single image. Let's look at a case where we have our image and our pixels are there. We do what we call contrast stretching. And the idea behind contrast stretching is that we want to redistribute our pixel values, because this will be a dark image or it will be a very bright image. Through contrast stretching, we can now redistribute. So you have your image. Sorry about that. So let's look at a case where we have our image, gives us a histogram. All of pixels are there, and we have already said this is 0 to 5. We have said this is a dark image. We can redistribute. We can redistribute. Yeah, we can redistribute, and then our resultant image is has more contrast. You could liken this to You could liken this to, what do they call it? Your remote when you're doing contrast. When you're doing contrast, there's that button for contrast. When you're adjusting, this is what you're trying to do to improve on the contrast so that you're able to distinguish between different features. So that's what happens when you're doing. That's what happens when you're doing contrast. So we have various techniques that we can use, and that is it about enhancement using one image. We can have our band. We can apply filters. We can also manipulate the. Histogram. Come up with the resultant image. We can have a case where we manipulate two bands. So we have our blue, we have our green, we have our red. Infrared, some infrared, and have a band there, band there, band there, and a band there. The whole idea behind that is manipulating two bands is that you have your band 1, we have band 2, so it can be 1 and 2, 3, 4, so it can be any of these, and by manipulating band 1 and band 2, we have a resultant image from the manipulation of band 1 and band 2. Now, for this to work, you need to have the same rows, columns. Usually, if it is the same image, you don't have to worry about that. They usually have the same rows and columns, and we can apply any mathematical operation. We can add, we can subtract, we can divide, we can multiply. So if this is A1, A2, A3, and this is B1, B2, B3, it will be A1 plus A. So if it is addition, it's addition that goes throughout. If it is division, it will be. How is this useful in remote sense? We mostly use this for what we refer to as, for example, development of indices. A good example is what we refer to as vegetation. Now, these are essential techniques that are used to make prominent vegetation in satellite images. And it comes from the fact that when we look at, we know the spectral signature of vegetation is we have high reflectance. We know that if you have sails, it will probably be something like that. And if we have a band in the near infrared and another one in there, you will see that the fact that vegetation has a low reflectance in the red and a very high in the near infrared, by getting the ratio of near infrared to red, we are able to make prominent. So I also like giving a fictitious figure. So I say that is 0.8. Here is maybe 0.4, 0.2, 0.1. And this is our reflectance. Can say vegetation, soil in red. Vegetation is say 0.1, whereas it is maybe 0.3. Soil is like 0.3. In the near infrared, we can see here we have 0.8 and or maybe 8 is 0.6. The near infrared gets the ratio of near infrared to red. We have 8, and here we have 2. So you can see that, yes, this is part of digital image interpretation. Yeah, so you can see that vegetation is made prominent by a factor of 8. These are fictitious values. So in this case, we are able to make prominent. Vegetation because vegetation has that unique characteristic of being low in red and very high in near infrared. So one of the most popular indices is what we refer to as the normalized difference vegetation index, which comes about because of special cases. For example, if you had water, let's give it red, blue, and we looked at its reflectance, you would see that water in the red is 0, and the infrared is 0. 0 divided by 0 gives us infinity. So as a result of that, we now have what we call normalized difference vegetation index, where you get your near infrared minus red over near infrared plus red. So this is an operation that enables us to make prominent vegetation. So we have different types of indices. So we have vegetation indices, we have built up area indices, we have water indices, we have salt indices, all sorts of indices are available. And when you have a built up area index, it is a combination of bands that enable us to make built up area prominent. I've had a student look at the salt in Katwe and how it is spreading, and he was using a salt indices, and selected one. So we can have vegetation index, we can have built up area index, we can have water index, and sometimes it's not only 2 bands, they may have more than 1 band. But the point is that we can combine 2 bands to come up with an improved image that gives us something more of what we want. The other thing I would like us to talk about, how we can enhance using 3 band. And how does it help us improve our image interpretation? We have our blue, green, red, near infrared. We have a band there, another one there, another one there, another one there. So if you got your, let's call this 1, 2, 3, 4. So we have our band 1, band 2, and band 3. We have our band 1, band 2, band 3, and then we projected band 1 on what we call the blue channel. So let's call this our channel. And we do this. This is the green, and this is the red. When we combine these 3, we get what we call a true, just like the satellite image that we have been showing now and again. So when we put the blue on the blue, the green on green, the red on red, get what we call color composites. And this is the idea what Earth would look like if you are looking at it from space. So we get the true colors of an image. We also have cases where now remember we have a band in the near infrared. So what happens is that let me use another color. We assign the near infrared. We assign red to the green, and we assign the green to the blue. And when we do that, we end up with what we call false color. Now, remember, vegetation has a high reflectance in red, and so in these images, bright red will mostly be vegetation. So if you have walked into an office and you see these big satellite images with a lot of red, that is probably a vegetation, and that's what we call a false color composite. And we use it a lot for vegetation studies. So these are the various ways in which we can manipulate our images to be able to extract information. We can enhance using 1 band, we can enhance using 2 bands, we can enhance using 3 bands. For those who are interested, I've said we can have a case where we have all the your land size, several bands. We can apply various operations. We can do principal component analysis. Those of you who have done a lot of mathematics, you can do into another space. We have different other spaces. You can do a Fourier transform and then do an operation in that space and then return. So these are, we can even, those days we used to do image fusion. We don't do it these days. And in any case, you do not have the time to do that. The idea behind image fusion is that you have a high spatial resolution image and a low spatial resolution image. We could combine them, come up with the resultant image with higher resolution. Not very useful these days since we already have high spatial resolution imagery, but that in a nutshell is what is possible. So today we have actually covered a lot. We have moved from visual interpretation, we have gone to digital interpretation. We have seen here how to manipulate 1 band. We've seen 2 bands. We've seen 3 bands. At different times, you'll be called upon to appreciate, use different combinations. And depending on our times next week, we shall be able to have some applications where we see some of these things come alive. I may get 1 or 2 people share their work, and you get to see how 1 or 2 or 3 or 4 or 5 of these methods can or have been used. I wanted we don't have the time today, but I wanted to share with you a link to a video which will contribute to your understanding of what we have covered. And yeah, that's the link. Please make time to watch, and that should pretty much give you a lot to do over the weekend. By next week, we want to be able to look at a couple of other things. I would like us to cover as much as is possible, so that at least you have some basic knowledge of image analysis, image interpretation, satellite images, what we can get from different satellite images, how to do some processing. I am hoping to get somebody to do some demonstrations or develop some content that you can do also all beyond the course. So are there any questions? Any questions? Okay. If there are no questions, I wish you a great weekend, and let us prepare accordingly.